All right, so this is multi-scale analysis and design of toe-steered composite structures using a mixed fidelity neural network model. I'm Clay Gifford, an undergraduate computer science major, and with me I have Shivani Pattar, who is a industrial manufacturing and systems engineering major. And our advisor is Dr. Jin Liu of the Industrial Manufacturing and Systems Engineering Department. And now I'll hand it off to Shivani.
So, the composite materials have been widely used in many aerospace structures. They have very good performance properties such as lightweight, high strength to weight ratio, better corrosion resistance, high design flexibility for complex structures, and also show low maintenance cost. Also, we have this newly emerging toasted composites, which are different from the traditional composites, which have curved fiber paths. They show improved structural performance. They have highly tailorable structural properties and also show reduced weight. In recent years, they have shown increased applications in aerospace structures. So the problem is that we don't have design tools to analyze these kind of structures and that we want to develop new models as well as lower the developing cost of these new models in terms of machine learning. So the overall objectives for our project are to develop a machine learning module using GUI plugin within Abaqus to generate simulation data in efficient way which will help us to train the developed machine learning model. Also, we want to develop a neural network model which will be trained based on the mixed fidelity data generated, and the goal is to have an accuracy of this model to be as close as the model which is fully trained by the high fidelity data, which will in turn reduce the training cost. So this is our first task. So basically, we designed a GUI window in Abaqus. The figure one shows the top menu button. When the machine learning is clicked, the window will appear as shown in the figure two, where the user will input all the parameters to define the neural network which we have generated. The figure 3 shows these parameters saved in a local file, and then this data will be used by the model later on to automatically create a new neural network model. So this is the design we want to use to generate this mixed fidelity data. So we have two different parameters, theta 1 and theta 0, and then we have used this function to describe the fiber paths. For example, my theta 0 is 10 degrees and theta 1 is 30 degrees, then we have a fiber path as shown in this figure. This is the path of this, the fiber paths are curved in nature here. Then we pick a structural example here to help us generate this design data. So here we have a one layer panel with all its edges fixed. And we applied a thermal load of 1 degree Celsius, and then we tried to find the critical thermal buckling loads. Then these two plots are the results which were generated from this analysis. Uh, Here we can clearly see that the thermal buckling load from high fidelity data and low fidelity data clearly show some difference with them. So next will be carried out by Clay. Yeah, here you go, Clay.
Thank you. Yeah, so as mentioned, we implemented a mixed fidelity neural network model. Um, and so this model is comprised of three neural networks. You can see in the top right here, we have the first neural network trained using low fidelity data, and then that gets coupled to two high fidelity neural networks, one with an activation function below that's used to exploit the nonlinear relationships, and then the second without a activation function. That's the one up above, and that's used to find the linear correlations. And then these two are brought together to bring us our final result. And we have an example here with some mixed fidelity data. So we've got 4 high fidelity data points, and then we've got 11 low fidelity data points. And these are the functions that were found to express the data for those data points. And then we would pass that through the neural network. So moving on to our actual implementation of the mixed fidelity neural network model, we've got our training data that was found with this function for the fiber path, and we've got 25 total data points for the high fidelity data, and then we've got much more, over 1,000 data points for our low fidelity data. And so our results are shown below, which shows a fairly linear relationship between the results with the high fidelity neural network and the results with the mixed fidelity neural network. And we were able to achieve similar accuracy while reducing the training cost by using a large amount of this low fidelity data as a substitute for some of the high fidelity data.
Okay, thank you, everyone.
Thank you.